Close your eyes for a moment. Imagine you are standing under a sky so clear that every star seems close enough to touch. The night is quiet, yet alive with secrets too small for the human eye. For centuries, people believed the universe was made of predictable clockwork parts, solid matter moving through space like gears inside a great machine. But in the last 100 years, we discovered something astonishing. Beneath the calm surface of reality, the world is ruled by hidden laws stranger than dreams. This is the story of quantum physics, explained slowly like a lullaby for the curious mind. The quiet birth of quantum physics. In the early 1900s, scientists began to notice cracks in the old picture of reality. The laws of classical physics could not explain why atoms glowed in certain colors, or why heat radiated in mysterious patterns. It was as if nature was whispering in a language no one had heard before. At first, these were just small puzzles, the kind researchers thought they could easily solve, but they were wrong. Max Planck, a quiet German physicist, proposed something radical in 1900. He suggested that energy is not smooth and continuous, but comes in tiny, indivisible packets. He called them quanta. To his surprise, this strange idea solved the mystery of glowing light from heated objects. Planck did not believe it himself at first. Yet his bold step cracked open the door to a new universe of thought. The birth of quantum physics was not loud or celebrated. It began almost reluctantly, with scientists feeling unsettled. Imagine standing at the edge of a forest at dusk, hearing unfamiliar sounds. That was how they felt. They were stepping into territory that made even seasoned thinkers uneasy. For reality itself was no longer what it seemed. Soon, young physicists like Einstein, Bohr, and Heisenberg entered the story. Each one carried Planck's idea further, building strange new rules about light, atoms, and matter. They were explorers, but instead of sailing oceans, they were diving into the invisible fabric of the universe. The more they looked, the less solid the world appeared. And so quietly, without parades or trumpets, quantum physics was born. It was not just a new science, it was a new way of seeing reality. From this point onward, nothing about the world could ever be taken for granted again. Light that behaves like a wave. For centuries, light was thought to be purely a wave. When you see ripples in water spreading outward, that's how people imagined light traveling through space. This picture worked beautifully to explain rainbows, reflections, and the bending of light through glass. In the 1800s, experiments proved beyond doubt that light made interference patterns exactly like rippling waves colliding on a pond. Think of two stones thrown into water. The waves overlap, creating bright and dark regions. Light does the same in the famous double-slit experiment. Where the peaks of waves meet, the brightness grows. Where peaks meet troughs, darkness appears. It was simple, elegant, and comforting. The universe seemed understandable through this wave picture. James Clerk. Maxwell sealed this view by showing that light is an electromagnetic wave, a dance of electric and magnetic fields moving together. His equations described light as energy rippling through space itself. For many, it felt as though light's mystery had finally been solved, until small cracks appeared again. Because if light was purely a wave, then why did some experiments show it striking matter in sudden bursts like bullets instead of ripples? Nature was hinting at a double life. The neat order of waves was about to clash with something far stranger. And so the stage was set. The wave story of light was only half the truth. Beneath the gentle ripples waited a sharper, particle-like secret that would shake everything we thought we knew. Light that behaves like a particle. In 1905, Albert Einstein asked a daring question. What if light sometimes behaves not like a wave, but like a stream of particles? He called these particles light quanta, later known as photons. To explain the photoelectric effect, where light knocks electrons out of metal, the wave theory failed completely. Only the particle idea worked. Imagine tiny beads of light striking like raindrops, each carrying a packet of energy. This was shocking. Scientists had grown comfortable with light as a smooth wave. Now Einstein was saying light could act like a shower of invisible bullets. It felt contradictory, almost impossible. Yet experiments agreed with him. The photoelectric effect became proof that light has a particle nature. The strangeness deepened. Light was not wave or particle. It was somehow both. How could reality wear two faces at once? Imagine someone who is both whisper and thunder, depending on how you listen. That is light. This paradox was not a mistake in thinking. It was the true face of the universe. Einstein's insight opened the floodgates. If light itself could not be pinned down to a single description, perhaps everything at the quantum level was just as fluid. Electrons, atoms, even the forces of nature might hide dual natures too. It was like discovering the world had been playing a secret game all along. And so quietly but firmly, the concept of particles of light took root. What began as a puzzle about shining metals grew into one of the pillars of quantum theory. The universe had revealed another of its strange smiles, the strange dual nature of reality, wave and particle. Two ideas that should not fit together, yet they live side by side in the heart of quantum physics. When light passes through two slits, it spreads out like a wave, but when you measure where the photons land, they arrive one by one like particles. The universe seems to decide in real time which mask to wear. This duality is not limited to light. Electrons, once imagined as little billiard balls, also show wave behavior. Fire them through slits, and they too make interference patterns as though they are ripples of possibilities spread across space. Then, when detected, they appear as sharp dots, as if the wave collapsed into a single point. The rules of reality are slippery, playful, and deeply mysterious. It forces us to rethink what things really are. Are particles solid? Are waves real? Or are both just different languages for describing something deeper that we cannot see? The answers remain unsettling, but in that discomfort lies wonder. The universe is not mechanical and flat. It is alive with paradox. To live in a quantum world is to accept that reality does not always follow common sense. It is layered, flexible, and sometimes contradictory. This strangeness is not an error in our eyes, it is the truth of nature itself. Reality is richer, stranger, and more beautiful than our minds first believed. And in this duality one can glimpse the hidden poetry of the cosmos. Light is both ripple and particle, dance and drop, whisper and spark. It shows us that the universe is not either or, it is always more. The mystery, hidden in the double-slit experiment. The double-slit experiment remains the crown jewel of quantum strangeness. When particles like electrons are fired at a screen with two slits, they do not form two clusters as expected. Instead, they create an interference pattern, as if each electron travels through both slits at once, interfering with itself like a wave. It is as though reality hesitates, holding many paths open at once. But the real shock comes when we try to watch which slit the electron goes through. The moment we observe it, the interference vanishes, and the electron behaves like a particle, choosing one path only. Observation itself changes the outcome. Reality shifts depending on whether we look or not. This raises haunting questions. What does it mean for something to be real if it only decides when observed? Does the universe exist in a state of pure possibility until attention collapses it into fact? The experiment whispers that reality might not be independent of us. that consciousness itself may be woven into the laws of physics. Some scientists resist this interpretation, preferring to think of it as just mathematics, not philosophy. But the mystery lingers. Why should mere observation carry such weight? What is the role of the observer in the theatre of the universe? The double slit keeps its secrets, daring us to look deeper. It is here, in this simple experiment of light and slits, that the heart of quantum physics beats most strongly. A child's setup of beams and screens reveals truths that shake the foundations of reality. And as we open more of this story, the mysteries only deepen. How observation changes the outcome. One of the strangest discoveries in quantum physics is that simply looking at something can change what it is. When an electron passes through the double slits unobserved, it spreads like a wave, a mist of possibilities. But the moment we measure its path, it collapses into a single choice, like a coin forced to land heads or tails. It is as if reality waits to be asked before it answers. This is deeply unsettling. In ordinary life, we assume the world exists whether or not we look. A mountain does not vanish when our eyes are closed, yet at the quantum level, observation matters. The tools we use to measure, tiny detectors, even beams of light, do not simply reveal reality, they disturb it. They force nature to decide. Looking is never neutral. Imagine a child watching fireflies in the dark. The moment she shines her flashlight, the fireflies scatter, their dance altered by her presence. The act of watching changes the story. That is what happens in the quantum realm. To know is to touch. To measure is to shape. Knowledge and interference are intertwined. Some physicists call this the observer effect. It suggests that the line between the knower and the known is not as sharp as we once believed. Are we just spectators of the universe, or are we participants, entangled with the play itself? This is not just science, it is philosophy, pressed into equations. And so each time we try to peek behind the curtain, we alter the script. Reality at the smallest scale is not fixed but responsive, as though the cosmos itself is aware of being seen. This quiet mystery will echo through everything that comes after, the birth of the quantum worldview. Step by step, the puzzles grew into a new way of thinking. Planck's quanta, Einstein's photons, and the mysteries of the double slit formed a foundation unlike anything before. It was as though the universe had been whispering riddles for centuries, and only now were humans learning the language. Classical physics described certainty, but quantum physics described possibility. This worldview did not come easily. The great minds of the time argued fiercely, sometimes late into the night, over wine, chalkboards, and restless debates. Was reality truly uncertain, or had they simply failed to find the hidden clockwork beneath? Some hoped the universe was still solid and predictable. Others felt they had glimpsed a deeper poetry. The quantum worldview says the world is not fixed until it unfolds. Electrons live as clouds of probability, existing everywhere and nowhere at once. Particles are waves, waves are particles, and the line between them blurs like mist at dawn. Even the act of asking shapes the reply. It is a worldview where certainty dissolves into chance. Imagine walking through a foggy field. Shapes shimmer, uncertain, until you approach. Only then do they solidify into trees or stones. Quantum physics says reality itself is like this, a fog of possibilities waiting for interaction to become real. It is not a flaw, it is the nature of existence. Thus, a new worldview was born, one that continues to ripple through technology, philosophy, and even spirituality. To embrace it is to accept that the universe is stranger but also richer than anyone dared to dream. Max Planck's tiny packets of energy. At the dawn of the 20th century, Max Planck faced a puzzle. Hot objects glowed with light in patterns classical physics could not explain. The old formulas failed. So Planck proposed a daring fix. Maybe energy itself comes in chunks, not smooth streams. He called these chunks quanta. At first it was just a trick to make the math work. But it opened a door no one could close. Planck's quanta meant that energy is like coins, not liquid. You cannot pay in fractions smaller than the smallest coin. Light, too, was made of indivisible units. This was deeply uncomfortable. Scientists wanted continuous order, not broken pieces, yet the universe did not care what felt comfortable. The data demanded quanta. At first, Planck thought this was a temporary patch, not a deep truth. But soon others, Einstein, Bohr, de Broglie, realized that Planck's quanta were the very heartbeat of reality. Atoms, electrons, even vibrations of heat followed this grainy law. The universe was pixelated at its roots. Picture a painting from afar. It looks like smooth color, but up close it is made of brushstrokes, dots of paint, tiny patches. Planck's discovery told us that reality itself is painted in strokes of energy, not continuous flows. The illusion of smoothness hides a granular foundation. From this tiny idea grew an entire revolution. Planck's quanta were not just math, they were the seeds of the strangest, most powerful physics humans have ever known: Einstein and the photoelectric spark. A few years later, Einstein took Planck's quanta and lit them on fire. He studied the photoelectric effect. When light shines on metal, it knocks electrons loose. Waves of light should have gradually built up enough energy like ocean waves eroding rock. But that was not what experiments showed. Instead, electrons burst free instantly, as though hit by tiny hammers. Einstein proposed that light comes in particles, photons, each carrying a discrete packet of energy. If the photon is strong enough, it knocks the electron free at once. If not, no amount of weak light will do the job. This was proof. Light behaves as particles, not just waves. It was bold, unsettling, even ridiculed at first. But over time, the evidence piled up. Photons became as real as bullets, as essential as atoms. The photoelectric effect was so decisive that it later won Einstein the Nobel Prize, not for relativity, as many believe, but for this humble quantum discovery. Think of sunlight striking solar panels today. The electricity that powers cities, homes, and satellites flows because photons strike metal, just as Einstein described. Each beam of sunlight carries quantum packets that set electrons dancing, lighting up the world. A century-old mystery became the backbone of modern technology, and so in chasing one puzzle about glowing metals, Einstein gave humanity both a deeper truth and a new source of power. From sparks on a metal plate to the energy of solar cells, the photoelectric effect remains one of the most beautiful bridges between quantum theory and daily life. The rise of quantum pioneers. After Planck and Einstein, a new generation stepped into the unknown. Niels Bohr built a model of the atom using quantum jumps where electrons leap between orbits without crossing the space in between. Louis de Broglie suggested that particles, like electrons, could also behave like waves. Werner Heisenberg crafted the mathematics of uncertainty. Erwin Schrödinger imagined the wave function that describes possibility itself. Together they shaped the new quantum landscape. These pioneers were not just scientists, they were dreamers navigating paradox. Their conversations were half mathematics, half poetry. They argued fiercely, was reality uncertain, or was it secretly ordered? Did waves describe something real, or only probabilities? Each man carried both conviction and doubt, chasing a truth no one could yet see fully. It was a golden age of thought where chalkboards became battlefields and lecture halls echoed with strange new terms: wave function, uncertainty, entanglement. Ideas that seemed like madness one day became Nobel-winning breakthroughs the next. It was as if humanity was collectively waking up to a dream beneath the surface of waking life. Imagine a group of explorers mapping a hidden continent. Every hill they climbed revealed more mysteries beyond. That was quantum physics in its early years. Each solved puzzle led to stranger landscapes. The pioneers often admitted they did not understand the quantum world. They were simply learning to describe it. And so, with Planck's spark and Einstein's flame, the torch passed to Bohr, Heisenberg, Schrödinger, and countless others. Together they built the strange, shimmering framework we now call quantum mechanics. And ahead in this video, we will step deeper into its mysteries. Atoms, the invisible building blocks. For centuries, atoms were only an idea. Whispered first by ancient Greek philosophers, then rediscovered in the age of science. They imagined matter as made of indivisible seeds, too small to see. By the 20th century, we knew atoms were real, yet quantum physics revealed they were far stranger than expected. Atoms were not solid marbles, but delicate structures woven from rules that defy common sense. Inside every atom is a nucleus, dense and powerful, surrounded by electrons. But electrons do not circle like planets around a sun. They live in ghostly clouds, spread across space like mist. Atoms are mostly empty, and yet from that emptiness arises the solidity of the world. The chair beneath you, the breath in your lungs, even your bones, all made of these invisible clouds. Atoms are restless. Electrons shift between states. Protons and neutrons hum with hidden forces, and the nucleus itself teems with binding energy. Nothing about atoms is still, nothing is permanent. What feels solid in your hands is really a storm of invisible activity, calm only at a human scale. Think of atoms as tiny orchestras. Each note is a particle, each vibration a field of possibility. Together they play the song of matter. Harmonies so small you cannot hear them, yet powerful enough to shape mountains and oceans. The universe sings through its atoms. And so, quantum physics teaches us that matter is not what it seems. The world is not built from solid blocks, but from patterns, probabilities, and energy clouds. Atoms are the doorway into the hidden realm where certainty dissolves into mystery. Electrons moving in cloud-like patterns. Electrons once puzzled scientists deeply. Early models imagined them orbiting the nucleus like moons around planets. But experiments proved this picture wrong. Instead, electrons exist as probability clouds, regions where they are likely to be found, though never exactly predictable. They are whispers of presence, not fixed objects. To describe them, we must think in terms of patterns, not paths. In these clouds, electrons form shapes, spheres, dumbbells, even intricate flowers of probability. These are orbitals, the architectures of atoms. Each element in the periodic table has its own signature arrangement of clouds, giving rise to chemistry, bonding, and the colors of the world. The entire diversity of nature, trees, oceans, stars, grows from these hidden patterns. An electron cloud is like fog drifting through valleys at dawn. You cannot point to a droplet and say, "Here is the fog," because it is everywhere and nowhere. Likewise, electrons are not tiny marbles circling in tidy tracks. They are spread out, smeared waves of potential. Yet when you measure, when you interact, the cloud collapses. The electron chooses a point, as if reality forces it into focus only at the moment of contact. Between observations, it lives in a twilight state, neither here nor there, but in between. This cloud-like life is the essence of the quantum. Electrons remind us the universe is not made of hard edges, but of flowing patterns. Solidity is born from fog. Predictability hides inside probability. What seems sharp is really soft. What seems fixed is truly fluid. Protons and neutrons in the nucleus. At the heart of every atom lies its nucleus, a dense cluster of protons and neutrons bound together by the strongest force known. If the atom is the size of a stadium, the nucleus is a grain of rice at its center, yet holding almost all its weight. This tiny heart carries the mass of the world. Protons are positively charged, while neutrons carry no charge. Their balance defines the identity of the element. Change the number of protons and you change the atom itself. Hydrogen becomes helium, carbon becomes nitrogen. The nucleus is the fingerprint of matter, setting the stage for life and stars alike. But what holds these charged protons together? They should repel, flying apart like magnets pushed against each other. Instead, they cling through the strong nuclear force, a binding glue that overpowers repulsion. Without it, the universe would dissolve into dust. With it, stars ignite and atoms endure. Inside protons and neutrons, the mystery deepens further. They are made of quarks held by gluons in a dance so intense it has no parallel in ordinary life. The nucleus is not just matter. It is an arena of seething, vibrating fields where forces battle and balance in silence. To think of nuclei is to touch the roots of creation. Every element in your body, forged in stars, carries a story written inside its nucleus. Each proton and neutron is a note in the cosmic song that birthed you. The quantum rules of atomic structure. Atoms obey rules that are nothing like the macroscopic world. Electrons cannot simply move freely anywhere. They are confined to energy levels like steps on a ladder. You cannot stand halfway between steps. The atom forces discrete choices. This quantization gives rise to the structure of the periodic table, to the colors of flame, to the chemistry of life itself. Pauli's exclusion principle adds another strange law. No two electrons in the same atom can share the exact same quantum state. This rule explains why atoms stack their electrons into different shells, creating patterns that define elements. Without this simple principle, matter would collapse, and life could not exist. These rules are not intuitive, but they are absolute. Electrons leap between levels by absorbing or emitting photons, quanta of light, in sudden, discontinuous jumps. They do not slide smoothly but vanish from one step and appear on another, like players in a cosmic game of hopscotch. Reality leaps instead of glides. Out of these leaps and rules comes chemistry. Carbon bonds, oxygen breathes, water flows, all because electrons arrange themselves according to quantum laws. The entire richness of the world, from DNA spirals to ocean waves, is born from this hidden logic. Atoms follow the quantum script, and life follows atoms. When you see a candle flame or hear the crackle of fire, you are watching electrons obey quantum laws. Even the simple act of breathing is orchestrated by atomic rules older than the Earth. Reality's most ordinary acts are quantum miracles in disguise. Why atoms do not collapse inward? Here is a mystery. If electrons are attracted to the positively charged nucleus, why do they not simply fall inward and collapse the atom? By classical reasoning, they should spiral down like satellites into Earth. Yet they do not. Atoms endure, stable, delicate structures lasting billions of years. The secret lies in quantum mechanics. Electrons are bound not just by attraction, but by rules of probability and wave behavior. They cannot exist arbitrarily close to the nucleus because their wave patterns forbid it. The uncertainty principle ensures that confining an electron too tightly makes its momentum unpredictable, keeping it from being pinned down. It is as though the atom protects itself with its own rules. This balance creates the stability of matter. Electrons hover in their orbitals, not because they want to, but because they must. Nature's laws create invisible barriers that prevent collapse. Atoms are delicate negotiations between forces, holding their shape not through strength, but through quantum compromise. Imagine a hummingbird hovering mid-air, wings moving so fast you cannot see them. The bird seems still, yet it is in constant motion. Electrons are similar. Their cloud-like presence creates the illusion of stillness, though they are sustained by restless, unseeable motion. Stability arises not from rest, but from constant balance. Without this quantum protection, matter would implode into nuclei, stars would not shine, and life could not breathe. The fact that atoms do not collapse inward is not just a detail of physics. It is the foundation of existence itself. And as we open more of this story, the secrets of energy, light, and life unfold further. The energy ladder. Inside atoms, atoms do not allow electrons to live wherever they please. Instead, they are confined to energy levels, a quantum ladder with rungs spaced apart. An electron cannot perch between two rungs. It must choose one or the other. This discreteness gives atoms their structure, their chemistry, and their character. The ladder is invisible, yet everything depends on it. Each rung corresponds to a quantum state. When an electron absorbs energy, it leaps to a higher step. When it releases energy, it falls back, glowing in the process. The colors of fireworks, the shine of neon lights, even the glow of stars are born from electrons climbing and descending these ladders. Each jump releases photons, quanta of light. Think of a harp. Each string vibrates at specific notes, never in between. Electrons, too, play only certain notes of energy. The atom becomes a silent instrument, strummed by the invisible hands of quantum rules. Its song is what we see as light, color, and warmth. The ladder explains why every element has a unique fingerprint of spectral lines. Thin bands of color, emitted or absorbed. Astronomers use this fingerprint to identify elements in distant stars. By studying the light, they read the ladders of atoms billions of light years away. The quantum ladder is not just theory, it is a cosmic language, so the atom is both prison and stage. Electrons cannot wander freely, but within their ladders they dance in brilliant ways. From these hidden rungs, the visible beauty of the universe is born. Quantum jumps, leaping without traveling. One of the strangest features of the atomic ladder is the quantum jump. When an electron moves between energy levels, it does not glide gradually. It vanishes from one level and reappears in another, without existing in between. This leap defies the smoothness we expect in motion. It is as though the electron teleports, instant and silent. Early physicists were stunned by this. It was unlike anything in classical mechanics. How could a particle leap without traveling the space between? Yet experiments confirmed it. The jumps are real, the leaps measurable. Quantum mechanics is full of suddenness, not continuity. Imagine standing on one step of a staircase and suddenly appearing 2 steps higher without ever touching the middle. That is what electrons do. In these leaps, they emit or absorb photons, packets of light that carry the energy difference. The world's colors, flames, and radiation all come from such invisible jumps. These transitions happen billions of times every second inside your body. The atoms of your skin, your breath, your blood are alive with leaps. Each quantum jump is tiny, but together they form the pulse of life itself. Stability and change coexist in this restless rhythm. The idea unsettled Einstein and others, but over time quantum jumps became the heartbeat of atomic physics. They remind us that the smallest world is not smooth like our own. It is sudden, surprising, and always alive with leaps of possibility. The glow of neon signs. explained by quantum physics. Walk down a city street at night and you may see neon signs glowing in vivid reds and oranges. That glow is a direct expression of quantum physics at work. Inside the glass tubes, atoms of neon are excited by electric currents. Their electrons leap to higher rungs of the atomic ladder, then fall back, releasing photons of specific colors. Every element has its own palette. Neon shines red-orange. Helium glows pale yellow. Argon radiates blue. The colors are not chosen by artists. They are dictated by the quantum structure of atoms. The sign is a gallery painted by physics itself, using light as its brush. Spectroscopy, the study of light, was born from these observations. Scientists used it to decode the fingerprints of atoms. In laboratories and observatories, they found that each glowing gas revealed hidden quantum rules. The universe itself became a spectrum of notes waiting to be read. Even stars obey this law. The same principle that makes neon light shine gives the sun its golden hue and galaxies their colors. By splitting starlight into spectra, astronomers can measure composition, temperature, and motion across unimaginable distances. The neon glow in a cafe window connects directly to the light of distant suns. What feels like decoration on a city street is in truth a cosmic truth displayed in glass. Neon signs remind us that quantum physics is not hidden. It shines everywhere, even in the humblest glow on a rainy night. The stars, shining through quantum processes, look up at the night sky. Every star you see burns because of quantum mechanics. Deep inside, hydrogen atoms are pressed so tightly they fuse into helium, releasing energy. But without quantum tunneling, the ability of particles to slip through barriers, this fusion would not happen. The stars shine because the quantum world allows the impossible. In fusion, protons must overcome electrical repulsion to merge. By classical reasoning, the barrier is too strong. Yet quantum tunneling lets them pass through, joining together in blinding release. Every sunrise, every glimmer of starlight exists because of this invisible rule. Life itself is powered by tunneling deep in stellar hearts. Fusion produces photons, quanta of light, which journey outward for thousands of years before leaving the star. By the time they touch your skin as sunlight, they have lived lifetimes inside. Each beam of light is a message from the quantum core of a star, written long before you were born. The colors of starlight, the warmth of the sun, the glow of galaxies, all arise from quantum energy levels, jumps, and tunneling. Without these processes, the universe would be cold, dark, and lifeless. The cosmos owes its brilliance to the smallest laws. Every time you feel sunlight on your face, you are touched by the work of quantum rules written in the heart of stars. The same physics that glows in neon tubes is burning across the universe, illuminating everything we know. Why the sky is quantum at heart? It may seem strange to say the sky itself is quantum, but it is. The blue of the daytime sky comes from photons scattering through air molecules. The scattering is selective. Shorter wavelengths, like blue, bounce more strongly than reds. This, too, is quantum behavior, rooted in how photons interact with electrons bound in atoms. At night, the twinkling of stars is shaped by quantum rules. Their colors reveal the jumps of electrons. Their brightness reveals the tunneling in stellar cores. Even the faint glow of the Milky Way is born from countless quantum emissions, blending into one soft haze. The sky is a canvas painted by quantum brushstrokes. Auroras shimmer in polar skies when solar particles collide with atmospheric atoms. Electrons are pushed to higher energy levels, then fall back, releasing green and red light. These curtains of color are quantum physics unfolding across the heavens, turning Earth into a stage for atomic theater. even cosmic microwave background radiation, the faint afterglow of the Big Bang, is quantum in origin. Tiny fluctuations of energy in the early universe were stretched by expansion into the seeds of galaxies. The sky carries in every shade and ripple the memory of quantum beginnings. To look at the sky is to look at quantum physics written large. From the blue above to the stars beyond, every shimmer is born of electrons, photons, and probabilities. The sky is not just vast, it is deeply, quietly quantum at heart. Heisenberg's uncertainty principle. Werner Heisenberg, a young physicist with sharp eyes and restless thought, uncovered one of the most unsettling truths of the quantum world. He realized that we can never know both the exact position and exact momentum of a particle at the same time. The more clearly you see one, the blurrier the other becomes. This was not a failure of instruments. It was nature's own rule. Imagine trying to watch a bird in flight at night. Shine a bright flashlight to see its wings clearly, and you disturb its path. Dim the light to leave it undisturbed, and you lose the detail. This tension is built into reality itself. At the quantum level, precision has a cost. Knowledge is always partial, always limited. Heisenberg's principle shook the scientific world. For centuries, physics had promised certainty, positions, speeds, predictions as sharp as clockwork. Now, with the foundation of matter, certainty dissolved, probability replaced prediction. It was as though the universe had drawn a soft curtain between what is and what can be known. Yet this uncertainty is not chaos, it is a balance, a built-in safeguard of the quantum world. Electrons do not collapse into nuclei because of it. Atoms endure because certainty is forbidden. Out of fuzziness comes stability. Uncertainty is not weakness, it is strength hidden in disguise. And so Heisenberg's insight taught us something humbling. The universe is not ours to pin down completely. Its truths shimmer, never fully captured. Reality itself insists on remaining mysterious. The limits of knowing, position, and speed. Picture an electron again. If you try to measure exactly where it is, its momentum becomes wild and undefined. If you try to measure its momentum precisely, its position melts into a fog. This is not a trick of tools, it is the very design of nature. The limits of knowing are written into the code of reality. This limit is unimaginably small at human scales. You can measure the speed of a car and its position on the highway with no trouble. But for electrons, photons, and quarks, the principle rules everything. The tiny world refuses to allow sharp answers. It breathes in probabilities, not certainties. The lesson is profound. At the smallest scales, reality is not a set of fixed truths, but a cloud of possibilities. Trying to lock both position and speed is like trying to catch both smoke and wind in your hands. One escapes as the other is grasped. The universe forces us to live with incomplete knowledge. Some see this as unsettling, but perhaps it is also freeing. The world is not a machine grinding away with rigid gears. It is flexible, uncertain, alive with chances. Life, too, mirrors this. We rarely know both exactly where we stand and where we are going. The fuzziness is part of the journey. Thus, the limits of knowing remind us of humility. The quantum world is not meant to be fully conquered. It can be described, danced with, understood in pieces, but never chained to absolute certainty. Why reality feels fuzzy, not fixed. When you look around your room, the world seems solid, sharp, dependable. But quantum physics whispers that beneath the surface, it is fuzzy, blurred at the edges. Electrons live as probability clouds. Photons exist as chances until measured. Reality at its roots is not fixed until it interacts, until it is forced into a choice. Think of dew on grass at dawn. Each droplet trembles, reflecting light in shifting ways. From one angle, you see brightness, from another, a shadow. Reality at the quantum level is like this: shimmering possibilities, never one thing until touched. It is not disorder, but a different kind of order, one that embraces uncertainty. This fuzziness explains so much: why atoms resist collapse, why elements form patterns, why light behaves like both wave and particle. If reality were rigid, matter could not dance, stars could not shine, life could not emerge. Fuzziness is not a flaw, it is the engine of creation. The unsettling part is how different this feels from our daily lives. We crave certainty, solid ground, yet the universe itself is built from uncertainty. What feels permanent is only the average of countless quantum flickers smoothed over at human scale. In this way, quantum physics reminds us solidity is an illusion born from foggy foundations. Reality feels stable because beneath it, countless uncertainties weave together into something that only seems fixed. Quantum probability, a world of chances. At its heart, quantum physics is a science of probability. It does not tell us exactly where a particle is or how it moves. It gives us odds, distributions, likelihoods. An electron has a certain chance of being here, another chance of being there. Reality is not a script. It is a roll of cosmic dice weighted by strange rules. This does not mean chaos. Probability has structure, like music played with variations. The equations of Schrödinger describe how these chances evolve in time. They predict patterns, not certainties. It is like forecasting weather. You cannot know the path of every raindrop, but you can know the shape of the storm. This probabilistic nature makes the world flexible. Atoms interact because electrons explore many possibilities. Chemical bonds form because probabilities overlap. Even photosynthesis in plants depends on quantum probabilities, guiding energy with astonishing efficiency. Life itself harnesses chance, not certainty. Think of it like waves on a beach. You cannot say where each drop of foam will land, but you can feel the rhythm of the tide. The quantum world has tides of probability that guide particles without fixing them. Reality is a sea of chances rolling endlessly. So when we say quantum physics is about probability, we are not admitting defeat. We are recognizing the deep truth. The universe does not run on rigid laws alone. It runs on possibilities, unfolding like music improvised moment by moment. Schrödinger's cat and living paradox. To show the strangeness of probability and superposition, physicist Erwin Schrödinger imagined a thought experiment now famous worldwide. Place a cat in a sealed box with a quantum trigger. Say, a radioactive atom that may or may not decay. If it decays, a mechanism releases poison. If not, the cat lives. After some time, before opening the box, quantum physics says the atom is both decayed and undecayed, and the cat, therefore, is both alive and dead. This was not meant to be taken literally. Schrödinger proposed it to show how absurd quantum rules sound when scaled up to ordinary life. A cat cannot be both alive and dead. Yet, at the atomic level, particles truly can exist in superpositions, in multiple states at once, until observed. The paradox raises haunting questions. Does observation collapse the cat's fate? Is the universe itself waiting for someone to look? Or is there another explanation, hidden worlds branching with each possibility? Schrödinger's cat is not about the animal. It is about the tension between the quantum and the human. Some interpretations suggest that superpositions are real but invisible, only collapsing when measured. Others propose many worlds where each outcome splits into its own branch of reality. The cat's fate is both, but in separate universes. Such ideas stretch physics into philosophy, but they remain part of the quantum debate. In the end, Schrödinger's cat reminds us how unsettling, yet beautiful, the quantum world is. It forces us to accept paradox, to hold contradictions, to admit that reality at its roots is stranger than we ever imagined. And as we open more, the paradoxes only grow deeper. Superposition, being in many states at once. In the quantum world, particles do not choose a single state until they are observed. They exist in superposition, a blend of possibilities. An electron can be in two places at once, a photon can travel two paths at the same time, a particle can spin both clockwise and counterclockwise. It is as though reality keeps every door open until the moment we knock. Imagine standing at a crossroads. In our world, you must choose left or right, but in the quantum realm, you take both paths at once, exploring them simultaneously. Only when someone looks do you collapse into one journey. This is not metaphor. It is how particles truly behave. Superposition is fragile. The moment of interaction, the brush of observation, collapses it into one definite outcome. Until then, the particle lives as a haze of possibility. This haziness is not ignorance. It is the very state of nature. Possibility itself is real. We see superposition in action in technologies like quantum computing, where qubits hold many states at once, allowing calculations beyond classical machines. Nature uses this principle too. In photosynthesis, energy travels many routes at once, ensuring plants capture sunlight efficiently. Life thrives because superposition is real. To embrace superposition is to accept that reality is not fixed, but layered, overlapping, shimmering. The world at its root is not this or that. It is both until the moment of choice. The collapse into a single reality. If superposition holds many states, then collapse is the moment of decision. When observed, a particle snaps into a definite outcome. The electron lands here, not there. The photon chooses this slit, not both. The wave of probability shrinks into a single point. This is what we experience as reality. But what triggers collapse? Is it measurement, interaction, or consciousness itself? This question remains one of the deepest mysteries of physics. Some argue collapse is caused by any physical disturbance, like a detector. Others wonder if awareness itself plays a role, if the universe needs observers to finalize its script. The collapse is dramatic, but silent. You do not see the wave vanish, you only see the result. It is like reading a book where, until you turn the page, the story exists in countless drafts. The moment you read, only one version survives. Quantum collapse is that turn of the page. It unsettled Einstein, who asked, "Does the moon exist only when we look at it?" Surely not, he insisted, yet the equations hold. At the quantum level, reality resists committing until something interacts. What seems obvious at our scale dissolves under the microscope of nature. Collapse is both an end and a beginning. It resolves superposition into fact, but in doing so, it reminds us how mysterious the act of observation remains. Reality seems to wait for contact before it settles. The role of the observer in shaping events. Whose kaito what taiwa is the observer? In quantum physics, the very act of measuring changes the outcome, but does this mean humans shape reality simply by looking? Or does any interaction, even a stray photon, count as observation? The role of the observer is still debated, and the answers remain slippery. Some interpretations suggest the observer is simply the environment. A particle's possibilities collapse when they interact with anything large enough to record them. Others suggest awareness matters, that consciousness is not separate from the universe but woven into its laws. In this view, the observer is not passive but essential. This idea has fascinated both scientists and philosophers. If observation shapes reality, then our role in the cosmos is not small at all. We are participants, not spectators. Each act of awareness may be entangled with the unfolding of the universe itself. The line between physics and philosophy grows thin here. But the mystery remains unresolved. Experiments confirm the effect, but not the meaning. Are we creators of reality or simply readers of it? Does the universe decide without us, or does it wait for our gaze? The observer's role lingers like a riddle without an answer. Whatever the truth, one fact is clear: observation matters. To look is to change. To measure is to interfere. At the quantum level, knowing and being are intertwined in ways that defy ordinary thought. The quiet debate between Einstein and Bohr, out of these mysteries rose one of the greatest debates in science. Albert Einstein, defender of certainty, clashed with Niels Bohr, champion of quantum strangeness. Einstein argued that the universe must be ordered, its rules precise and complete. Bohr countered that nature itself is probabilistic, that uncertainty is not ignorance but truth. Their conversations shaped the soul of physics. Einstein could not accept that God plays dice with the universe. He believed hidden variables must exist, unseen rules waiting to be discovered. To him, quantum mechanics was incomplete, a map missing its details. He respected the equations but resisted their meaning. Bohr, by contrast, embraced the paradox. He insisted that quantum mechanics was not incomplete, but simply different from classical thought. The limits of knowledge were not failures, they were the very fabric of reality. Probability was not approximation, it was the language of the cosmos. Their debates grew legendary. In smoky rooms and crowded conferences, they exchanged thought experiments and counter-arguments, each refusing to yield. Einstein would craft challenges, Bohr would find answers. The duel was intellectual, but it was also poetic. Two visions of the universe clashing in silence. Though Einstein never accepted Bohr's interpretation, history sided with Bohr. Experiments confirmed quantum predictions again and again. Yet Einstein's doubts kept alive the search for deeper truths. Their debate remains alive, echoing in every modern discussion of quantum theory. God does not play dice, or does he? Einstein's famous phrase, "God does not play dice with the universe," captured his unease. To him, a universe ruled by chance was incomplete. He believed hidden order must exist even if we had not found it. Nature, he thought, could not be rolling dice in the dark. For Einstein, the cosmos had to be rational, not whimsical. Bohr replied gently but firmly, "Einstein, stop telling God what to do." To Bohr, the dice were real and the universe truly probabilistic. The randomness was not ignorance, but woven into the structure of reality. This clash of views became more than science. It was philosophy disguised as physics. Over time, experiments proved that probability rules at the quantum level. Entanglement, tunneling, uncertainty all confirmed that chance is not illusion, but law. Still, Einstein's discomfort continues to resonate. Even now, physicists wonder if deeper layers of order lie hidden beneath the dice, waiting for discovery. The metaphor of dice speaks to us beyond science. Do we live in a universe of strict fate, or one of chance and possibility? Quantum mechanics suggests the latter. But perhaps chance itself is part of a grander order, one we cannot yet see. Dice may roll, but the table may still have a design, and so the question lingers, does God play dice? Or is chance the only language vast enough to hold the universe's complexity? The answer remains open, suspended like the particles themselves. And as we open more of this story, the mysteries only deepen. Quantum entanglement, spooky connections. Imagine two particles born together, like twins who never lose their bond, no matter how far they drift apart, across a lab, a planet, or a galaxy. They remain mysteriously connected. Measure one and instantly the other reflects the result, as if they whisper faster than light. This is quantum entanglement, one of the strangest discoveries in science. Einstein called it spooky action at a distance because it defied common sense. How could information travel instantly, breaking the cosmic speed limit set by relativity? Yet experiments kept showing it was real. Entangled particles behave as though they are not two, but one system stretched across space. The mystery is not just speed, it is about unity. Entangled particles do not carry hidden instructions like prearranged answers. Instead, they seem to share a single identity, responding together no matter the distance. It is as if the universe itself refuses to separate them. Entanglement is fragile. Any disturbance can break the link. But when preserved, it is astonishing. Today, scientists use entanglement in labs to teleport quantum states, to create secure communication channels, and to imagine the future of quantum computers. What began as spooky has become technology. To grasp entanglement is to see that separation may be an illusion. What we call distance may not exist at the deepest level. Beneath the surface, the universe might be one indivisible whole, endlessly connected. The invisible thread-linking particles. Think of two dancers moving in perfect harmony, even when placed on opposite sides of the world. Every step of one mirrors the other's rhythm. Entanglement is like this, but without music, without signals, without delay. The connection is invisible, unbroken, woven into the fabric of reality itself. When particles are entangled, their properties, spin, polarization, momentum, become linked. Change one, and the other adjusts instantly, even if no communication is possible. It is not that one particle tells the other what to do. It is that they are no longer separate things. They are parts of one larger pattern. This invisible thread cannot be seen, but it can be tested. Again and again, experiments confirm the effect. Detectors on different continents, satellites orbiting Earth, even beams split by mountains show the same eerie connection. The universe allows threads that stretch without breaking. The implications are breathtaking. If particles can be linked across distance, then perhaps information, memory, or even reality itself is not local, but spread out. What feels separate to us may be joined in ways our senses cannot detect. The universe may be more web than machine. So the invisible thread of entanglement whispers of hidden unity. Beneath all division, there may be a deeper togetherness binding particles, and perhaps everything, into one. Einstein's discomfort with spookiness. Albert Einstein, despite being one of the fathers of quantum theory, could never accept entanglement. He believed the universe must follow local realism, that objects have definite states, and nothing can influence something else faster than light. To him, entanglement was absurd, a sign that quantum theory was incomplete. With colleagues Podolsky and Rosen, Einstein posed the famous EPR paradox, arguing that entanglement meant either instant communication or missing pieces of physics. Surely, he thought, hidden variables existed, unseen instructions carried by particles to explain the spooky results. Quantum mechanics, in his view, was only a half-truth. But experiments decades later proved Einstein wrong. Entanglement violated the expectations of local realism. No hidden instructions could explain it. The particles truly behaved as though distance did not matter. It was one of the rare times Einstein's intuition faltered in the face of data. Yet his discomfort was valuable. It kept physicists questioning, testing, probing. Without Einstein's challenge, entanglement might have remained a curiosity instead of a central truth. His doubts sharpened the science, giving rise to experiments that confirmed quantum mechanics with stunning precision. Einstein never fully embraced entanglement, but his resistance became part of the story, a reminder that even great minds can be unsettled by the strangeness of nature. His discomfort still lingers in ours whenever we ask, how can the world really work this way? Bell's theorem and the end of hidden variables. In the 1960s, physicist John Bell took up the challenge left by Einstein. He asked, can hidden variables explain entanglement? He built a mathematical test, now called Bell's theorem. If particles carried secret instructions, their correlations would follow certain limits. But if quantum mechanics was right, the results would break those limits. Experiments began. At first, crude, then increasingly precise, they tested entangled particles. Time after time, the results violated Bell's inequality. Hidden variables were ruled out. Entanglement was not a trick of ignorance. It was real, fundamental, undeniable. The universe does not behave like Einstein hoped. Bell's theorem was revolutionary. It transformed philosophy into physics, argument into experiment. For the first time, questions about the nature of reality could be settled not in debate, but in laboratories with detectors and photons. The verdict was clear: the quantum world plays by rules stranger than hidden variables. This was unsettling, but liberating. Physicists could no longer cling to the hope of underlying certainties. Instead, they embraced the paradox. Reality itself, at the deepest level, does not separate neatly into parts. Bell showed that wholeness is not an illusion, but a requirement of physics. Thus, Bell closed a chapter and opened another. Einstein's dream of hidden order faded, replaced by the mystery of unity. The universe proved itself spookier and yet more wondrous than even its greatest minds imagined. Experiments that proved entanglement real. From the 1970s onward, laboratories around the world designed tests to push Bell's theorem to the limit. Photons were split and sent in opposite directions. Electrons were paired and measured apart. Each time, the eerie correlations appeared. Entanglement was not theory. It was fact, confirmed by countless trials. In the 1980s, Alain Aspect's experiments in France closed major loopholes. Later, in the 21st century, even stricter tests using satellites and long-distance fibers proved entanglement across kilometers, even hundreds of kilometers. The spooky action was not a lab trick, it was universal, unstoppable, woven into the laws of nature. These experiments showed something profound. Reality does not divide neatly into local parts. The outcome of one measurement is linked instantly to another, regardless of distance. The universe, at its root, does not care about separation. Connection is deeper than space itself. Today, scientists harness this for technology. Quantum cryptography uses entanglement to create unbreakable codes. Quantum teleportation transfers states across distance without moving matter. Each breakthrough confirms that entanglement is not just strange, it is useful. The universe's weirdness becomes humanity's tool. The story of these experiments is a reminder. What began as an unsettling paradox grew into proof, then into practice. Entanglement is not just a curiosity, it is the most intimate truth of reality, echoing across science, technology, and philosophy. And ahead in this video, we step further into instant correlations that stretch across vast distances. Instant correlations across vast distances. Entanglement shows us something almost magical. Particles remain linked no matter the distance. If two photons are entangled, you can send them to opposite ends of the Earth, and still their properties mirror one another instantly. It is not about signals traveling and nothing is sent. It is about unity deeper than space. They act as one even when far apart. This idea unsettles us because distance feels so real in our daily lives. A whisper cannot cross an ocean without time. A letter cannot reach another city without delay. Yet entanglement ignores these barriers. The universe behaves as though space does not separate, as though distance itself is an illusion at its root. Experiments prove it again and again. Satellites beaming entangled photons to distant labs show perfect correlations. Detectors split by mountains register linked results. No matter how far, the connection holds. Nature insists that entanglement is not bound by ordinary limits. The question lingers, what does this mean for the fabric of reality? Is space truly as empty and separating as it seems? Or is it stitched with hidden threads that keep everything connected? Entanglement suggests the latter, that unity runs deeper than division. In this way, the cosmos reminds us, separation is not the final truth. Beneath the distance lies instant correlation, a silent signal of wholeness that defies every common intuition. Why entanglement doesn't break causality? Entanglement may seem like faster-than-light communication, but it is not. You cannot use it to send a message instantly across space. The outcomes of each measurement are random. Only when compared later do the correlations appear. This protects causality, keeping the universe safe from paradox. Spookiness does not mean broken rules. Think of tossing two dice that are magically linked. Each throw gives a random number, but when compared, they always match in a strange way. You cannot choose the result of your die to send a signal to the other. The match only shows when both are revealed. Entanglement works like this. Mysterious, but never a loophole for faster-than-light talk. Einstein's relativity still holds its crown. Nothing material, no signal, no energy moves faster than light. What entanglement shows is not transmission but correlation, a unity so deep that distance does not apply. It is as if the particles never fully separated, as if they still share one silent identity. This balance is elegant. The universe allows wonder without chaos, mystery without contradiction. Entanglement stretches imagination but preserves order. The cosmic dice roll strangely, but they never break the table on which they fall. So entanglement does not break causality. Instead, it reshapes our idea of connection. It tells us that the universe is more unified than we thought, yet still consistent, still whole. Entanglement, inside your smartphone technology. Entanglement may sound abstract, but its fingerprints are already in your daily life. Quantum effects power the semiconductors in your phone, the lasers in your internet fiber, and the GPS that guides you through the world. While full entanglement devices are still young, the principles that grew from it already shape modern technology. In labs, entanglement is being harnessed for quantum cryptography, secure communication where keys are shared through entangled particles. If an eavesdropper tries to listen, the entanglement collapses and the intrusion is revealed instantly. It is security written by physics itself. Quantum teleportation is another marvel. Using entanglement, the state of one particle can be transferred to another across distance without moving the particle itself. It is not teleporting matter but information, yet it may one day revolutionize communication networks. Even quantum computers rely on the spirit of entanglement. Qubits are not just isolated superpositions. They are linked, entangled, weaving together possibilities that allow computations beyond classical reach. Entanglement turns the strangeness of nature into power we can use. So when you scroll through your phone or connect to Wi-Fi, remember, the seeds of this everyday magic were planted by entanglement. The spooky has already become practical, already lighting the screen in your hand, the possibility of a quantum internet. Imagine a network not built from ordinary signals, but from entangled particles. Messages shared not through cables alone, but through correlations that cannot be hacked or forged. This is the dream of a quantum internet, a future where communication is secured by the laws of physics themselves. Researchers are already taking first steps. Satellites have distributed entangled photons across continents, Labs have teleported quantum states between cities. Each experiment builds the scaffolding for a new kind of network where information is not copied but entangled, not transmitted but shared in unity. Such a network would be unbreakably secure. Any attempt to spy would destroy the entanglement, alerting both sides. Trust would no longer be a human agreement. It would be written in nature's deepest rules. Banks, governments, even personal communication could one day rest on this invisible shield. The quantum internet would also connect quantum computers across the globe, weaving them into a single machine of unimaginable power. Problems that defy today's computers, drug design, climate modeling, cryptography, could be tackled by networks of entangled processors. It may sound like science fiction, but every year the dream grows closer. The same spooky action that puzzled Einstein now hints at a future where the entire Earth hums with quantum connection. A universe that may be one whole network. Entanglement whispers something profound. If particles can remain linked across distance, perhaps the entire universe is one vast entangled web. At the Big Bang, everything was once connected. Perhaps those threads still hum beneath the surface, binding galaxies and particles in silent resonance. This is not proven science, but it is a tantalizing thought. If true, then separation is only an appearance. Every star, every planet, every person would be strands of one cosmic network. Distance would be an illusion draped over unity. Even today, some physicists wonder if space-time itself emerges from entanglement. The geometry of the universe, the fabric of space, may be woven from quantum connections. If so, then entanglement is not a side feature. It is the loom on which reality is woven. Think of a spider's web glittering with dew. Each thread is delicate, yet the whole structure holds together, vibrating as one. The universe may be just such a web, vast, shimmering, entangled at every point. Our sense of individuality, of separateness, may be only one way of seeing, and so entanglement becomes not just a feature of physics, but a metaphor for existence. Perhaps we are not alone, not isolated, but part of one great network of being, a universe entangled with itself.